I'm very pleased and honored to have Professor Fefferman from Princeton University. Just to say something that Professor Fefferman is, first of all, a graduate of the University of Maryland. But beside that, Professor Fefferman is also a winner of the Filmmakers and Steve Salem Prize. And we are very pleased to have him, and we all know that he's going to talk to us about interpolation and extension of smooth.
Thanks. All right, so thank you. I'm always very happy to come back to the University of Maryland that did so very much for me. Actually, when I think about who has done, who has given me real help to be an institution, I think immediately of the University of Maryland and of Roy Stein, sitting over there. And so this is a special moment for me. All right, now, all right, so on the one hand, there is that. On the other hand, I'm going to speak about something that I have spoken about many times before. I heard in one of the previous talks the determination not to give the same talk twice, and I'm afraid that standard has fallen by the wayside a long time ago for me. So in particular, I feel sorry for my undergrad students. I wonder how many times they've heard this stuff. I'm going to try to give a talk which is not quite isomorphic to the talk that I've been giving for the past long time. And in particular, I would like to look, not just to state theorems, but to sort of look inside the machine and explain a little bit how some of it works. Okay, let me explain the problem. Well, maybe first I explain the goal. In the broadest terms, the goal is to do something useful. It has been, I think, so one of the virtues of this conference, which I think has been quite remarkably successful, is that it really brings pure and applied people together. And what you're going to see is an attempt by a pure mathematician to do something useful. So I'm not there yet, and that's why I keep plugging away at the same set of problems. All right, so what is the problem? All right, so let me not talk about extension of functions just yet. If there's time at the end, I'll say something about extension of functions, but let me concentrate on interpolation. Now, so the idea is going to be that we're given a function at finitely many points. Maybe we're given this function exactly, maybe we're only given this function to a certain accuracy, and then we want to interpolate, and we want to produce some nice smooth function, as smooth as possible, that agrees with the data. As smooth as possible, that means that we're working in some function space. So we need to pick a function space, and there are lots of interesting ones, but the only spaces in which I can tell you any theorems are either Cm of Rn, or let's say Cm alpha of Rn, where, so let's say these are Cm functions whose nth derivatives are Lipschitz of order alpha, or a little more generally, so Lipschitz of order alpha means something or other is less than t to the alpha, and there could be some more general function of t. Let me call that omega, and so by analogy with Cm alpha, there's something called Cm omega that right now we won't even define. But for the moment, let's just work in here. So until I say otherwise, all m and n are fixed. All norms are going to be taken in that space. And when I say things like a constant depending only on m and n, that's m and that's m. Okay, so it's simply a constant depending only on m and n depends only on which function space we're working. Okay, so we are interpolating data. Let's specify the data. So this can be relaxed, but let's say that our functions are real value. Okay, E sits inside Rn, and it's finite, and so the number of points of E is capital N. And I would like you to think that little m and little n stay fixed and are not very big. Maybe we're interested in C2 or C3 of R2 or R3. But this capital N is enormous. We are given 1 billion points. Okay? And now, perhaps I'm interested in functions that on Rn, functions in Cm of Rn that agree perfectly with little f, maybe not so perfectly. Since it may be not so perfectly, I'm going to specify also another function. Let's call it sigma 0. I will often forget the sub-zero. Please remind me. So this is going to take e to, let's say, the non-negative real numbers. And the significance of this is that, let's say, there is some underlying function, and you are an experimenter, and you have performed experiments on what this function does at each point of the set E. And your experiment has yielded an experimental value of f, but it has also led to an experimental error of sigma 0, which maybe you know in this. Okay? Now, I would like to find a function. Well, I would like to find a function f in Cm of Rn, and let's say a number m positive, such that the following conditions hold. First of all, the norm of f in Cm of Rn is less than or equal to m. Okay? The second thing I would like to do is that for each one of these finitely many points, I would like to say that the capital F differs from the experimental value to within m standard deviations. And so this is supposed to be true for all x in E. It's a little strange that there's the same number m here as here. There are reasons why that's convenient for the mathematics that will follow, but just in the statement of the problem, that is unnatural. But on the other hand, I didn't tell you what sigma 0 means, and if you want to put a different constant here in place of m, all you have to do is rescale sigma 0, and the problem hasn't changed, the m has become the same. Okay? So, modulo that little point, this is a very natural problem. Now, what does it mean, find f? Find. Well, what I would like to do is to exhibit an algorithm to be run on a computer. Okay? And so this computer should, this algorithm should take E, little f, little sigma 0, and of course little m and little n, and then the algorithm should grind for a while, and it should compute for you the function capital F. Now, if I have time, I will tell you more precisely what that means, right? Computers work with finitely many bits, and if we're not being extremely careful, we can think that computers work with real numbers, but computers don't work with functions. So what does it mean to compute a function? I owe you an explanation, and I think I may not give you one. Okay. But instead, I'm just going to say that we are very interested in how many computer operations it takes our algorithm to succeed. It's all very well for me to stand here and tell you that that there is an algorithm and it will compute and so on and so on and so on. But if it takes too many computer operations, it's of no use. And the ultimate goal is to do something useful. Okay? So, all right. So, all right. It turns out that this problem is very closely connected with questions of extension of functions that I said I'm going to suppress in this talk, but it's connected with some mathematics with which maybe, let's say, 7 or 8 years ago, I had just finished working out, felt very happy about, and then, aha, this is related to it, right? And so I found a nice algorithm to solve this problem. I felt pleased with it, but then when I showed it to Boas Klartak, he immediately showed me a much better way to do things, and so we have a joint, two joint papers, and I would like to, explain to you what we do. So, all right, we're trying to find these. Now, of course, independently of how good our algorithm is, it would be nice if this m is not so enormous, right? So what we're going to do is we will compute, so we compute a function f and a number m satisfying these conditions. Such that the number m here is less than or equal to c times the least possible n. Where this c depends only on little m and little n. Okay? And where the number of computer operations needed is at most c n log n. Where again this c also depends only on the number of operations. Okay? Let's see. Except that I haven't told you, well, you know what, maybe I should take 5 minutes and tell you what it means to compute a function and say a little more precisely what this is. So a function consists of course, of infinitely many numbers. Right? So what does it mean to compute a function? Let me describe what really happens in this algorithm. It's what I'm going to take as the definition of a computing function. So we're going to enter the data into a computer. So we enter the little m, the set e, the function little f, the sigma 0, and then we're going to press go. All right? On the screen, the computer will say, "Thank you, I'm thinking about it, please wait a while." The computer then executes an algorithm. Okay? That algorithm takes at most cn log n computer operations. It then writes on the screen, "Thank you for waiting, I have computed an answer." Well, that's all very nice, but now you would like to probe and check whether the computer has actually done anything. And so at that point, you may query the computer. And so you sit at the table, you sit at your terminal, and over and over again, you type in the coordinates of a query point, of your favorite query point. Oh, computer, you have computed the function capital F. Here's a point. What is the function value at that point? The function is supposed to be Cm. Fine. Tell me not only the function value, but please tell me the function value and its derivatives up to order m at that point. And when you type in a query, the computer says, "Okay, please wait just a sec." And then very quickly the computer comes back. It has executed a query algorithm, and it outputs the function value and the derivatives up to order little m at that query point. Okay. Now, all right. So when I say the number of operations needed is at most that's what I said before I told you what's really going on. I really need to tell you 3 numbers to specify what's really going on. How much one-time work is there that the computer, before the computer says, "Okay, I understand." That's the cn log n. That's the one-time work. Then there is the query work, so that when you subsequently enter a query, tell me about this particular point, the computer has to execute some algorithm in order to compute the function value and its derivatives up to order m. Okay, and that's the query work, and that is this is, I should say, this is for the one-time work. One-time work. Okay. Let's come up here. C log n query work. And one other number, namely, this computer has a memory, and we had better not overtax the memory. And so we need enough memory in the computer, and the memory, the size of the memory that we need is Cn. These constants C depend only on little m and little n, and I claim that that sounds very good. So first of all, how much work can it take to solve this problem? We had better look at all the data before we give the answer. That requires work n, simply to look at every data point. Well, we're bigger than that only by a factor of log n. There are many, many problems in computer science that require at least n log n work, but from, let's say, the practical point of view, trying to do something useful, n can, everybody knows n can be very big without log n being very big, and so this means that this could be a practical algorithm. Okay. How about the query work? Notice that it is very important to keep the query work down. One-time work you only do once, but I sit at the terminal and type in lots of queries. Or perhaps maybe I'm interested in using this function for some other purpose. Maybe I really want to compute its integral over a domain, and so I will feed this information to some numerical integrator, or who knows what. And so it's important that once the one-time work has been done, the work to answer a query is very small. And again, except for a logarithm, I mean, the computer has to at least type out the answer, which takes a number of computer operations of the order of 1, and this is worse than that only by log n, so we're in good shape there. And the computer memory needed is only Cn, and simply in order to hold the statement of the problem, you need work n. So this is, I believe, a real serious practical problem being addressed, and so one could then ask, is this a real serious practical algorithm? And it looks from everything I've said as if the answer is yes, but in fact the answer is a resounding no. Let me explain why. And so that's why after proving this result in 96, 2006 or so, that the problem is still with us. Okay. There are these constants that depend only on little m and little n. That's all very nice for mathematicians, but if we want anything useful to come out of this, we are somewhat interested in how big these constants are. Okay. Well, I called them all C, but they're all different. This C is actually not very big. This C is actually not very. I'm sorry. This C is actually not very big. This C is not very big. This C is very, 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 very big. Okay. So the algorithm is not practical. I will be very interested in trying to find a practical algorithm. Let me stress one other thing before I start to tell you a little something about how the algorithm works. Okay. Namely, I'm not interested here primarily in algorithms that work if E has some kind of nice geometry, if it's a perfect lattice or a deformed lattice or something like that. I want this to work for a completely arbitrary set E. So under the worst possible conditions, it should still work. Okay, and that makes the problem much, much harder. I don't want to get into details. All right, now.
One quick question.
Yeah, sure.
So what happens if E has some structure? Would that make it any easier?
It probably would make it much easier. Now you could ask, what is the definition of success? So a definition of success is to do exactly this, but where all of these constants C are not very big. Okay. If the set E has some structure, that's surely a doable problem. I think people actually do that today. Okay. On the other hand, one could ask a more demanding definition of success. Suppose that you are part of, let's say, part of the problem. In addition to these data, part of the problem might be an epsilon positive given to me, and my job is to find a pair like this for which the m is as small as possible up to a factor 1 plus epsilon. That problem is a great beast. I'm just in the process of writing up a solution for the case little n equals 2, little n equals 2. That can also be done, and the number of computer operations is like that, but the constants depend on epsilon, but damn it, they depend very badly on epsilon, and so it's still not practical. Okay. For that version of the question, even if E has a lot of structure, it's still hard. Okay. All right. Any other questions before I go on?
So Joe, in case of quantum, doesn't depend on sigma.
That's right. That's right.
So I thought if sigma is big, you should be wrong.
So if the sigma is big, you will have more freedom, and therefore you will be able to take the m smaller, and it will affect what the f is. But at least the way this algorithm works, it doesn't affect how how many computer operations are required, and it doesn't affect the bounds we get for the ratio between our m and the best possible m. But by the way, tiny footnote, when I say least possible, it's an nth in elementary examples, it isn't an nth. It's an nth. Yes?
Have you thought, what if you just perturb the set? You're given an arbitrary set, but maybe if you're looking at a set which is close to it and has more structure, maybe that would work somehow.
Let's see, in unfavorable, okay, so the answer to your question is no, I have not thought seriously about it. It's a very reasonable question. There are many problems of great interest in which one gets to pick the set E, or in which one has some freedom to pick the set E. In delicate cases, so I don't have time to explain what's a delicate case and what's a trivial case of this problem, but in delicate cases, it's a highly unstable problem, and little changes in the set E make a big difference.
Thank you.
Okay, any other questions before? Okay, so how does the algorithm work? Okay, in as little detail as possible, I would say there are two main steps. The first step is to define and compute certain convex sets, and then the second step is to use them. Okay? Now, let me talk first about defining and computing the convex sets for two reasons. The first, so first of all, well, for multiple reasons. I guess if we don't have straight what the sets are, it's not going to be very easy to use. Let's see. I claim that these convex sets are interesting in their own right, and that if we care about this problem, we should equally well care about computing these convex sets. They're almost at the same level of interest as this. Okay. Furthermore, with a limited time, I'm pretty sure that I will be able to explain something about how to compute the convex sets. I'm much less confident of being able to explain anything about how to use them within the time. Okay. So what are these convex sets? So let's say we're interested in pairs f and m satisfying this. Now, a little bit of notation. Suppose I have a function f, and suppose I have a point x. This j stands for jet, and jx of f is simply the mth. Actually, let's call that the nth order Taylor polynomial about x. Okay, so this polynomial, what information does this polynomial contain? It contains exactly the function value at x and its derivatives up to order n. Okay, all right. And this belongs to a vector space that I'll call script P for polynomials. This is simply the vector space of all polynomials of degree less than or equal to little m on Rn. Of course, real polynomials. All right. Now, what is the set? What is the convex set that we're going to compute in order to solve the interpolation problem? I'm going to call it gamma of x n. And this is the following. Let's look at all possible functions f and numbers m. Well, this m is the same as this m is the same as this m. Okay? So I'm interested in functions f which for this given m satisfy condition star. Okay? And for all such functions, I ask, what is the Taylor polynomial of such a function f at the point x? The set of all possible Taylor polynomials of f which satisfy this condition I want to call gamma. This is a convex subset of the vector space P. Okay. So notice, of course it may be empty. I don't know whether there is any f that does this. I may be greedy. I may demand that m is very small, so small that there is no interpolator. And if there is no f, then this gamma will simply be the empty set. So gamma may or may not be empty, but it's convex. By convention, let's say the empty set is convex. If you think carefully, I'm not sure this is true, but I believe it's true. If you think carefully about the definition of the convex set, the empty set is convex. Yeah. Okay. This is clearly a convex set, right? Because given any two points, given any two functions f that satisfy this condition for a given m, you can take a convex combination of them, and it will again satisfy the same condition, and therefore it's a convex set. Okay. All right. Now, I claim that this is an important convex set. We should care about it. Let me explain why. All right. And so I'm going to bring in my car. Okay. So it's an old car. It's been in a traffic accident. It doesn't run so well. All right. If I get into my car, I am guaranteed that there is a bound on the acceleration and a bound on the velocity. Okay? If I keep it's not a Toyota. Okay. All right. And so therefore there are bounds on the C2 norm of think of position as a function of time. There are bounds on the C2 norm. Let's say m is the bound on the C2 norm. All right. Now, suppose that I tell you that initially my car was in my driveway. All right, my driveway is, well, so let's say I'm on a straight track. Initially, I'm very close to some starting point. And then, let's say, at certain discrete times, I tell you with varying degrees of accuracy where my car is. Okay. Now, once all of that has happened, then I ask you, okay, consider some other instant of time. Maybe even it's one of the moments when I told you what the position is. Let's say every 10th of a second, I tell you where my car is with an accuracy of 1 inch, whatever that means. Let's think there's one particular dot painted on my car, and that's the position of my car. So I tell you with an accuracy of 1 inch where my car is. Okay. And then I ask, at this particular moment of time, what can I say, given all that information, what can I say about my position and my velocity? That's a very natural question. That's, of course, only the one-dimensional case. That's for functions of one variable, functions of time only. But my question is to compute a particular gamma of xm. Right? M is the information that my car can't accelerate very fast and can't travel very fast. And x is the particular time at which I want to know what's going on. And I ask, okay, what are the position and velocity, and for that matter, acceleration of the car, given the constraints and given the information that I know with certain accuracy where my car is at 100 discrete moments of time. That's a very, very natural question. We should be able to answer it. The one-dimensional case is a nice exercise. The n-dimensional case, as far as I can see, is a serious theorem on the same level as the rest of the stuff that I'm discussing. Okay, so what we're going to do is to compute gamma of xm. We are not going to compute it perfectly, but we're going to compute it approximately in the sense that there will be a convex set that we actually exhibit, let's say gamma computed. And we will find that that the following is true, that the gamma of xm, the real gamma of xm is comparable to the one we compute in the following sense. Here we've got a small constant and a big constant here, and these constants depend only on little m and little n, that is on the space we're working in, and in this sense, we're computing what's going on. So that is, I don't have completely precise information for you, depending on the fact that our speed is less than 43 miles an hour as opposed to being less than 50 miles an hour. It's not that precise, but nevertheless, there's a big difference between being able to go, between being able to go at 50 miles an hour and being able to go at half the speed of light, and that sort of thing is captured by this. Okay, so in that sense, I would give you an efficient, give you a way to and this is computed. So these computed convex sets essentially capture the character of the gamma. Okay, so now I have defined the gamma. I'm going to tell you how to compute it, and then if there were more time, maybe I could tell you how to use it. Okay, so how do we compute this thing? All right, so I'm going to erase. Let's just remember we're given these, and I'll just write down again the definition of gamma. Inductive construction. So the induction proceeds on an integer L. So for each L, for each positive integer L, non-negative integer L, we're going to define a set gamma of x Lm, which is a guess for gamma of xm, right? But the guess isn't necessarily right, at least right away. It's going to be too big, but it's the idea is that this set is clearly going to contain this one. Okay, and so it's going to be defined by induction. So first, what happens when L is 0? And I'm simply going to define gamma of x 0m to be the set of all polynomials in this vector space P. All polynomials in P such that P of x, this same x, minus f of x, is less than or equal to m sigma 0 of x, and the derivatives of p at x are less than or equal to m. Okay. Now, notice that any polynomial in here obviously lies in here. What I've done is I've taken let's say this is only defined for x in E. This makes sense and is actually interesting for x not in E, but for the moment, let me just restrict attention to this. So this represents the information that I have if I ignore all points except this one? Well, of course, that's throwing away almost all the information, so this is highly unlikely to be the right thing, but it contains the gamma. All right, now points are going to talk to one another. So, all right, let me now erase this. Okay, and now imagine that I've fixed gamma. I'm sorry, I've fixed L. Let's say L is greater than or equal to 0, and let's imagine that I already know the sets gamma of x, L, M for all x in E. Right? Suppose I already know that, then I will define gamma of x, L plus 1 M. That's the induction. And this is for all x in E. And the idea is that points talk to each other. If I have 2 points of E, especially if one of them is very close to another, and I know something about the Taylor polynomial here, that tells me something about the Taylor polynomial here. What does it tell? All right, so an aside. Suppose that the norm of f for some function f is less than or equal to m. And suppose that I'm given 2 points x and y in Rn, and let's say p is the Taylor polynomial of f at x, and let's say p prime is the Taylor polynomial of f at y. Okay? Well, Taylor's theorem tells me that partial alpha of p minus p prime at, let's say, x is less than or equal to some constant times m times x minus y to the m minus alpha for alpha less than or equal to m. Where, notice there's some stupid degeneracy if x equals y and alpha equals m, and in that case I declare that this thing means 0. Okay? So simply that's what Taylor's theorem tells you. All right. No, this is p minus p. So for instance, let's take, it is, it's just. Okay, so, all right, now let me exploit that little observation in order to find this gamma. So I'm going to say that, all right, so let p in gamma of x, L, M, we will say that p is in gamma x, L plus 1, M, if for every y in E, there exists p prime in gamma of y, L, M, which we already know when we pre-computed this guy, such that absolute partial alpha p minus p prime at x less than or equal to that same constant m x minus y to the m minus alpha for alpha less than or equal to m. That's my definition of gamma of x L plus 1 y. I'm sorry, gamma of x L plus 1 x. Notice, notice that this is computable. I don't want to get into issues of how many operations and how this should be modified, but this is a very explicit definition. Okay? I can compute this set. And notice, thanks to this operation, the following is true. Imagine that we already know that all these guys are too big. That is, they contain, imagine all of them contain these gametes. All right? Then it follows that these guys are also too big. They also contain the real gametes. Because if I take any p in the real gamma, it is the jet of some function at x. And then, in order to see that there exists a p prime, I just take p prime to be the jet of that same function at y. And this condition holds because it's just Taylor's theorem. Okay? So these things in principle can be computed. All right. Right. Okay. So we have in principle some very elementary machine where we can turn the crank and obtain smaller and smaller and smaller convex sets which are guaranteed to contain gamma. Well, they could be all empty. If any of them are empty, then in some sense we've understood the problem. If any of them are empty, then we say, aha, clearly there is no interpolant, we can go home. Okay? All right. All right. So now let's assume that we have done this for a while and all of them are non-empty. Okay? And then the theorem is the following. So let's see. All right. So obviously, by induction, by the way this thing is designed, gamma of x, L, m contains the real gamma without any index. Right. This is the one we want to find over there. This contains that. That's obvious. Okay. Less obvious. Okay, there exists a constant L, an integer constant, depending only on little m and little n, such that gamma of x, L, m is contained in gamma of x, c, m. And this constant also depends on little n and m. But damn it, it's enormous. But it depends on little n. So in principle, this theorem tells us that for just turn this crank enough times and then declare victory, and the gamma that you have computed is essentially the gamma that we want. All right? The proof of this theorem is equivalent to the step in the algorithm that says use use these gammas in order to find the function f. Now, all right, I see that I've been speaking for 45 minutes, and I should be speaking for up to 50 minutes. So this suggests that I should not tell you how to use the gammas. I'm sorry. All right. Instead, I think it might be fun to spend 5 minutes explaining a very, very nice idea from computer science, which enters into the proofs of the theorems. Okay. Here's the remark. So 30 seconds of the 5 minutes go to saying the following. Okay. This is all very nice, but it could not possibly lead to an algorithm which is as efficient as the one I promised you. Because here, every point y is talking to every point x. And so if the set E has n points, it will take at least n squared operations to allow every point y to talk to every point x. And so there's no way that this can lead to an operation, to an algorithm that takes n log n steps. There is a much easier version of this problem, which was solved by computer scientists in a very beautiful way. And I would like to explain that for 1 second. In the remaining time. So let's ask a much easier question. So we have a set E in, let's say in the plane. It can be in array. Oh, all right, it's in array. Right? 10 points. Capital N points. Think of this little n as being fixed, this capital N as being arbitrarily large. Now, I give you a function little f from E to, let's say, the reals. Okay? Now, let's not try to extend it, but I simply ask you to compute the Lipschitz constant of this function. And so the Lipschitz constant of f, by definition, the max over all pairs x and x prime in B, different of, let's say, f of x minus f of x prime divided by x minus x prime. Okay? Compute that. Of course, that's trivial. For each x and for each x prime, you look at that, you look at that, you subtract, you take the absolute value, blah, blah, blah. It's trivial. And it takes n squared steps. Well, so trivially computed. In n squared steps. Okay. Less trivially, we can compute it up to, say, a 10% error. This is in n log n steps. N log n operations. By a very clever algorithm. And that clever algorithm is called the well-separated pairs decomposition. And I have 2 minutes to tell you the underlying idea. So I'll tell you the underlying idea and then perhaps. So let's look at two subsets of E. This is the set E prime, this is the set E double prime. And let's imagine they're well separated, which means that the distance between any one of these points and any one of these points is at least 10 times the distance of any 2 points here, and at least 10 times the distance of any 2 points here. Well separated. Okay? Now, let's look at the max of absolute f of x prime minus f of x double prime over x prime minus x double prime, where the x prime is restricted to lying in here and the x double prime is restricted to lying in here. We could compute this in the obvious way by looking at each possible x and each possible x prime, and then the number of operations would be the product of this number of points with this number of points. But there's a much smarter way. I'm sorry? Yes. In fact, all right, so hold on, all right, well, so notice, first of all these distances are essentially the same. So we only compute that once. How about this? How is this maximum achieved? Well, either we take that as big as possible and that as small as possible, or vice versa. So really, we don't need to look at all pairs, we just need to find the max and min of these and the max and min of these. And the number of operations needed to do that is the number of points here plus the number of points there. Therefore, for fixed E prime and E double prime, the number, there's a big win. Okay? If you can take the Cartesian product of E with itself minus the diagonal and cut it up into not so many of these, you can make that big win. Even that is not the optimal thing. The optimal thing to do is, having made that partition, look at each of these, pick 1 point here and 1 point here, just one, and compute just this one thing. For any particular E prime and E double prime, you may have made a gross mistake, but the maximum of all the things that you compute turns out to be the right answer. And I don't have time to explain why. That's a separated pairs decomposition. Okay, thank you.
I have a question. Suppose I have a function and you tell me that in these two rooms in front of me, there's one of them is your algorithm, the other one has a fake algorithm. Do you know how many queries I would have to make to figure out which room I was in?
Right, so, here's an example of a fake algorithm, right? I will take some little tiny cube which does not meet any of the data points, okay? I will now, the fake algorithm takes our algorithm and executes it, but modifies the function very slightly on this little cube. It will take me a hell of a lot of explanation of exploration to figure out which room I'm in. So it's a reasonable question, but it needs we need some more quantitative way to pose it, or else the answer is there's no limit to how much.
So there's a theorem saying there exists a L such that the gamma XLM is containing gamma XCM, right? I want to
Yes.
know, can you quantify that L is like how far you need to go in order to make it precise?
Okay, so let's see. I'm trying to remember how it goes. Oh, all right, maybe I should say that question is so simple. I should ask my graduate students. if you happen to remember. Here,
I think it's
here's our
exponential.
exponential.
Due to the n.
There you are. There you both are. Do you happen to know?
Kevin, is it exponential?
Yeah. Okay. All right. If you read carefully the paper that the papers that Boaz and I wrote in 2006, it's in there, and it's pretty big. I think that it is big enough that it is not. I mean, it's not going to. No practical algorithm will use it. However, it is possible that given the vast majority of real problems, you can stop much earlier. Okay. But I don't know. I haven't done any exploration of what this means.
The proof of that theorem you stated, you think that's a homework problem or too hard?
Which theorem?
The one you stated, and then
The one, about the gammas.
yes.
All right. All I can say is that if you do it as a homework problem, I really want to see your solution. Okay. It's